Hi class, we are starting introductory chemistry. This is chapter 1. I've broken this up into 2 different videos. Normally I will break these up into one section. So if it's 1.2, normally there would be a video for just 1.2. However, some sections are really small and I join them with others. One thing to remember here is I try to give examples to problems, and this is being recorded well before this is being recorded over Christmas break. I do not have access and they have not given me the homework. I don't choose the homework problems. I have nothing to do with the homework problems. The department chooses them and they release them when the semester starts. That's a little bit of a problem because I can't give you sample problems because I don't know what the homework consists of. Now there's generally, chemistry doesn't really change across, any books and if it's introductory, there's usually the same content in there. But some stuff's a little bit more challenging than others, and I would have liked to have seen that. But it will, as it gets released, and I can fix this future sections that are coming up. So not necessarily in this video, but in the next one I do have examples and samples to help try to understand the content I cover in this. So let's get started. Chemistry. Chemistry is basically understanding substances, what they are made of and how they behave and how we can use them with this knowledge. Chemistry is a central science. It is connected to other fields of science. If you are, I was a chemistry major. That's my degrees are in. And I had to take other, physics, a lot of physics classes. And so everything is pretty much connected to each other. And when you go take one class, you will start understanding where some of that overlaps with the other one that you're studying, such as chemistry. So chemistry basically, I apologize, I'm also a little sick, so I might be rambling some. Chemistry overlaps with many disciplines is pretty much what it is. And it may not make sense at first, but as you start taking these classes, you'll see where they all start connecting. So matter, everything is made of matter. Chemistry is the study of matter and its changes. So if we look at this dog over here, if we start going inside the layers, you'll eventually get to molecules, which you may not understand what that term is yet. And then we'll get to an atom, a single atom that makes up this dog. Everything is made up of atoms. Everything is made up of matter. So once we get past the matter, we're interested in going to inner and inner layers until we can actually look at the atoms themselves. So matter is material that makes up all things. It has mass, and mass is similar to the definition of weight at this moment. It'll change when we cover that chapter. And it has space. It occupies space or has volume. So in this chapter, we're going to briefly go over this here, this chart. This chart is not in your book. This is some of the pictures I use here. If you look for them and you don't see them in your book, it's because I took them from other chemistry courses that I teach. This is just a brief overview. We will go over this more in other chapters, but they want us to start bringing this out now. So I decided to show this chart because it would make a little bit more sense as to what we're covering. So here's matter, and matter is everything. We start categorizing matter to help us understand it better and to combine it with other things that actually are part of that. So the first things we have are pure substances and mixtures. We're going to cover this at the end of this video. We're going to start on this side because this helps understand the other side. So composition and structure. Composition. So when we're looking at matter, we start looking at the substance's composition and structure. Composition is what something is made of. So it's composed of. And structure has both. It considers what something is made of, but also not just what it's made of, but how is it arranged. That makes a big difference because diamonds are made of carbon, but so is also graphite. So how they're arranged really makes a difference of what it is we're looking at and how we can use it. So these pics here are a good example. These are a deck, a canoe, and a baseball bat. They all are made of wood. However, the structures are different. The wood is arranged to the function that's needed for it. And that's what we want to look at is that, yes, these are all wood and they were cut to be made in different structures. But when we start looking at atoms and molecules, the molecules and the atoms, they're arranged that way on their own, but they are all from the same, for instance, like carbon. Diamond is made of carbon and so is graphite, but the arrangement of the atoms makes them different materials. Pure substances. Pure substances. matter is anything that occupies space and has mass. It's composed of atoms. So we're going to start with atoms so you understand what an atom is. An atom is the smallest unit of an element that retains the chemical properties of the element. So what do we symbolize it as this spherical, this one little cylinder, this little ball, or a two-letter symbol, and this is chlorine, or the two-letter symbol and the orb or tiny sphere. This represents one atom. What does this do? Well, if we look at this gold bar here, this gold bar is made of only gold atoms. And if we take all these atoms away, eventually we'll get to one atom that's left. That is the smallest unit of an element that retains the chemical properties. Now we can break open this atom, and we will learn about that later, but it's no longer a gold atom. We are dealing with subatomic particles. They don't have the same properties of that atom. So when we get to the bottom, if we have a hill and we move everything away of atoms till we get to that final atom, that is the smallest unit that retains the chemical properties of whatever element we're looking at. So we depict this as a sphere, and that's what you're going to start seeing is spheres, and they're colored. The colors means different elements. So if you understand a periodic table of elements, which you probably don't, but excuse me, I think almost everybody has seen one. Those are all different elements up there, and they're all different colors to show that you are combining different elements together. So that's why if you see here, we have a pure substance. It is strictly copper. There's nothing else here but copper. They're all copper pennies, and it's all one color to indicate you're only dealing with copper atoms. Now we get to compounds and, So we did element, so we covered the element. So now we're going to jump over to compounds. Okay, so molecules are a group of atoms bound tightly together and behave as a single unit. So we take these atoms and we bind them together with other atoms, and that's where you see the different colors. Now, these are under pure substances because we do not have anything else involved except for those compounds. When in chemistry, and I am an organic chemist, I've worked in the lab for many years, you don't deal with just water. You deal with impurities inside the water. That's why you have your shower heads and everything it turns white, because there's a lot of impurities, a lot of compounds that you don't want in there, and that's what makes that look that way in your shower. So when we're talking about compounds here, we're strictly talking, for example, water, straight water, no impurities, no nothing to it, just H2O, two H's and an oxygen. And that's why if you look in this corner, you can see it. This is a compound. There's our three atoms joined. Two of the atoms are the same. So it's a group of atoms that are bind together. And we see this not as a hydrogen, or an oxygen. We see this as one whole unit. It is combined, not to be broken apart. So that's what it means behaves as one unit. Now, that's a molecule. Molecules are under compounds. A compound contains two or more elements in a definite ratio. That's where water comes in. No matter where you are in the world, you can take a sample of water, and water will always be H2O. It will not change. That's a definite ratio. There's a 2-to-1 ratio of 2 hydrogens to 1 oxygen. Now, if I have H2O2, I have hydrogen peroxide. There's a ratio of 2 hydrogens to 2 oxygens. That's a definite ratio. That's the name for that compound. That's what definite ratios means. Nothing's random. They have set ratios. Think of that like an address. That address goes with that water, and no one else can take that address, or fingerprint if you want. So we have hydrogen peroxide. That's a compound. Water is a compound. Table salt is in sodium chloride, and table sugar. Now here's the thing. Not all molecules are compounds, but I'm going to cover that later. So right now we're just going to say molecules are part of compounds, and compounds are atoms that are grouped together in a definite ratio. So you see these numbers. This means there's 12 carbons, 22 hydrogens, and 11 oxygens. This is that address or fingerprint. That's how you know that it's sugar. Now some molecules are grouped together in two. They're the same color, so they are the same atoms. We have hydrogen, nitrogen, and oxygen. They are only found paired up in nature. They are naturally two molecules, where most elements, if you find them, you technically don't find them by themselves. But some molecules, hydrogen, nitrogen, and oxygen, these are gases. are paired up. So it's H2N2O2. Excuse me. So that's what diatomic means. Diatomic means two molecules joined together. And in this case, we're only looking at this point at same atoms that are joined together. There are actually 7 elements that are diatomic molecules, but right now your book's only brought up these 3, so I'm going to bring up these 3. This image shows 4 molecules of oxygen. Remember, we treat this as one whole unit. We treat this as one whole unit. So this is a unit, this is a unit. So that's where it says 4 molecules of oxygen. When you hear the word molecules, you know that it is more than one. And each molecule in this case contains 2 oxygens that are bound together. Now, if we look at composition of materials, if this is copper, then this is strictly all copper atoms. But the water that's going through is a molecule. It's a molecule of water. So basically what this is showing is that when we look past the macroscopic level, macro means world, what we can see with our eyes, and we start looking at things on the microscopic level, we're looking at the atoms. We're interested in what's beyond what we can see with our eyes. And this copper, this pipe is made out of copper, so all we would see is copper elements. If it's a pure substance, we would see nothing else in there. In the water is a compound. So an element by itself is not a compound because it's only one atom. A compound has 2 or more, and this is a molecule. Water is a molecule. It has 2 hydrogens, 2 atoms. But both of them are pure substances because they have nothing else involved in them. They are strictly, water has nothing else involved or attached. There's nothing there. It's just H2O. And copper is by itself all one atom. Okay, now we're on to mixtures. And mixtures are a little bit more complicated because everybody wants to put everything into elements and compounds. Elements is one. Remember that. It's just one. One of something and it's all the same. Nothing else. Compounds are 2 or more, but there's nothing else there and they are attached to each other in a certain way that we see them as one unit. What makes this different than mixtures? This is where some people have problems starting out. A mixture is a type of matter that consists of 2 or more substances that are physically mixed but not chemically combined. 2 or more substances in different proportions, not bound in fixed ratio. And I will give examples to show this. Substances can be separated by physical means. Mixtures of metals are called alloys. So if we look at bronze here, bronze is a mixture of copper and tin. They are physically mixed together, but they are not chemically attached to each other like as water is. We can change the ratio. We can alter the ratio of copper to tin or other metals to determine how we want this to look. So for instance, we can change the hardness or the color of it because we can change the ratios. We may not understand. This is where it's like, well, you see it there. Yes, it is bronze, but the mixture itself is different. It's fixed ratios. Somebody else that will make the statue out of bronze will not have the same content or ratio, fixed ratio. That's something that I would make. There's not a fix there. Probably not explaining this better. So let me get to some examples and show you what I mean. Homogeneous and heterogeneous. So we started at mixtures. They are physically mixed but not chemically combined. What does that mean? We're going to look at homogeneous and heterogeneous. A homogeneous mixture is a composition is uniform throughout. Vinegar is a perfect example of something that is physically mixed, but not chemically combined. So that means they're not attached or attracted to each other. They consist in the same solution, but we can separate them out and not lose what they were on their own. You can't do that with compounds. We can't break up water without spending a lot of time and energy into breaking up water back into hydrogen gas and oxygen gas. But with homogeneous and heterogeneous mixtures, we can. So a homogeneous mixture, I'm going to try and make this as simple as possible, is one layer. One phase is what they call it. What does that mean? Well, if you look at vinegar, you don't see the acetic acid. You don't see the water. You see one phase, one layer. So you don't know where the acetic acid is in here and you don't know where the water is. They are mixed together, but they are not chemically combining to each other. They're not attracted to each other. They're in a room because they're locked in the room together, but they don't really care about each other. The different parts of the mixture are not visible. So that's why I call this one phase, one layer. Your book doesn't say this way, but this is how I've learned it and it's made things a little easier. This is also known as a solution. So when we refer to a solution are homogeneous mixtures that are not chemically combined, but they're physically mixed together, stuck in a room together. You cannot see the differences of each other, but they're there. Heterogeneous is a lot easier because you can see the differences. This is what I call two or more phases. You can visibly see the different phases. It's not uniform throughout. So in this case, the compositions vary from one part of the mixture to another. The different parts of the mixture are visible. Something would be like a chocolate chip cookie. You can eat one part of the cookie and you might get a few chips, and you can eat another part and you get no chips. That is what the difference is of the mixture. Here we see sand separated from water, but there's two layers. There's two phases. This is oil and water. There's two phases. But here, salt and water, we don't see it. It's one phase. That's a homogeneous mixture. If you cannot see more than one phase, it's a homogeneous. If you see more than one phase, it's automatically a heterogeneous mixture. Because homogeneous, the word homo is uniform. It's one throughout. So this is different. You can see it with your eye where you cannot visibly see it. Punch would be another one. You can make different concentrations of punch. That is a homogeneous mixture because you cannot see the little, unless you over put more punch into it. You don't see the difference. It's uniform throughout. It's just a mixture, but the concentrations will never be the same depending on who makes it. It's not a fixed ratio. So here's other examples of mixtures. We have chocolate chip cookie. As you see, it's a heterogeneous because you can visibly see two layers. Here we have coffee. Let's just dump these. Well, these two on top are heterogeneous. These two on the bottom are homogeneous. So here in this picture, you see a white solid being poured. Well, it's a clear solution, but the minute it comes in contact with this other solution that looks like water, it starts turning white. That means it's not mixing. The white is pulling away from the water, it doesn't like the water, and it is changing to a color. That means, and then what they're saying is on the atomic level, what you'll see is that there will be regions of water and there will be regions of this white solid, and they will try to stay far away from each other. So this is a heterogeneous mixture because you can see two phases. Homogeneous. Coffee is a homogeneous mixture. You do not see what's involved in it. The coffee and the water are mixed. You cannot see the differences in them. And people like different concentrations of coffee. So this is not set. Air, the air we breathe, is a homogeneous mixture because you do not see that we mainly consist, what we're breathing in is mainly consist of two elements. Nitrogen takes up 78% of our atmosphere and oxygen is only 21%. We breathe in nitrogen, but it does nothing to us. It just comes out. Oxygen is what we need, and 21% is very good for us. Trust me, you don't want it more than that because oxygen is very flammable. Things would be catching fire left and right. But our air is a mixture. It is a homogeneous mixture. We also have 1% that makes up water vapor and other traces of other gases that are in the air. And depending on where you live, the water vapor might be higher. If you go to Mojave Desert, it might be a lot lower. So this is why it's a homogeneous mixture. We don't see it. You don't see that nitrogen and oxygen is in the air, but it's a mixture of mostly two gases. What makes mixtures different than pure substances? Because mixtures can be separated. We can separate mixtures out. Mostly heterogeneous mixtures. We can separate water from sand because you can get something like this. And if we were in person, you would do something like this. We would get the water and the sand. And this is called filtration. You pour the mixture of the water and sand through this filter, and the sand will remain behind, trapped in the filter, but the water will pass through. We have now separated this mixture out, and we did it very easily because the substances are not attracted to each other, not creating a bond, so they can very easily separate from each other. And once we separate them, they are still the same. They have the same identity they had before. Compounds cannot do that. We cannot separate water back into hydrogen gas and oxygen gas without a lot of work putting in. Yes, it can be done. Yes, it does happen, but it's got a lot of things behind it to make that happen because that is not something that would commonly occur. So again, these are samples from another chemistry class that's equivalent to yours, but without seeing the homework, I cannot give you samples. So I'm just giving you what I think you guys might have in your homework at this moment. And if things change, I'll make another video related to the homework. Identify each of these following as a pure substance or mixture. So I'm just going to jump and give you everything so we can break this down. Pasta and tomato sauce is a mixture because of the fact that it is 2 layers. We can see this. Aluminum foil is a pure substance. It's an element because it only consists of one atom type, and that's aluminum. Helium is a pure substance because it's only helium atoms in the helium gas. And air is a mixture because air consists of oxygen, nitrogen, and 1% of other gases in the air. Identify each of the following as homogeneous or heterogeneous mixtures. Hot fudge sundae, I'm just going to jump ahead. Hot fudge sundae is 2 layers or more than 2 layers. It's 2 layers or more. So that is a heterogeneous mixture. Shampoo. Do you see anything in it? No, you see one layer. So that is, depending on which one, if you only see one layer, then you have a homogeneous mixture. Sugar water, you do not see the sugar. You do not see the separation from the water. It is a homogeneous mixture. It is one layer. Peach pie. You see the pie, you see the peach inside the pie. I did not bring up peach pie. I don't even think I've ever had peach pie. I took this from another book. But you see the 2 layers?